Good afternoon and welcome to the latest SOMTech Sonar, where today we will be talking about solving real-world problems with 3D spatial surveys using ADCPs, and take a look at a case study based on the River Severn in Shrewsbury in the United Kingdom. If at any time you have any questions, please use the icon on the GoToWebinar interface down, it should be on your bottom right. Submit a question down here and we will do our best to try and answer your questions at the end of the session. So my name is Nick Martin. I work for Xylem Analytics UK, specialising in SOMTech products, some of which you see on the screen at the moment. We have a couple of side lookers on the left, flow tracker in the middle, and a River Severn M9 on the right-hand side. We also provide YSI, Ondera, and WTW instrumentation as well. Today is a very special day for us, and we're very pleased to announce our partnership with the team at WaterCube for the UK. Joining me in this presentation will be Diana Krupa, who is one of the CEOs of WaterCube, and also Professor Art Smith from the University of Illinois. Unfortunately, John Sloat, who is the CTO of WaterCube, cannot join us today as he is travelling. I'd now like to hand over to Diana.
I am so pleased to be here and to announce this partnership with Xylem. And I thought I'd give a few introductory slides to just discuss what WaterCube is and why you would want to cube it. So WaterCube is a solution, really, to address the needs of the water resource industry and be able to provide a solution, a total workflow, which enables customers to have an aggregation of their data on the water using multiple instruments and utilizing a big data processing engine such that it is processing and analyzing vast amounts of river reservoir data, and then software on the back end to visualize and manage that data for comparative analysis, for validating and measuring your progress. So this is something that we can do within days of data collection. No longer do you have to wait for a DEM to be created or to utilize MATLAB or ArcGIS or separate software applications. You can now process very quickly, create spatial views, and have your data within days. And the applications are really quite vast. Today we're going to be focusing on velocity indexing and site selection and calibration with Art Smith. But we're also going to talk a little bit when we start looking at this data about the power of spatial data and what it can truly provide for certain applications, whether you're looking at stream power for hydropower applications, flow and quality monitoring, site selection, river restoration, even doing bathymetric studies in reservoirs and sediment buildup studies, habitat studies as well for your environment. And another thing that's quite unique with our Cubeit software is the ability to do model calibration for your numeric and hydrodynamic models and compare real spatial data to your numerical models and to calibrate them more effectively. So technology has come quite a long way, and that's what's really enabled us to bring this solution to the market. So, in the 90s, there was the ability to get out on water and collect information through a single frequency Doppler ADCP. And then into 2000s, the invention of a multi-platform integrated ADCP was a vast improvement and enabled everything to be within one system, giving you coordinate systems and the information you needed. And today, we're able to put multiple systems on the water. Not just one, but multiple can be used, and then we can aggregate this from multiple ADCPs, as many as you wish to put out there, and collect that, pull it together, and process it very rapidly so that you can visualize your river like never before. So with all this technology, of course, there are still challenges. And so for looking at how you want to solve the objective at hand, there is a lot of technology that still has to come together, be applied to the water, and a methodology for the data collection. And so Nick will walk us through that in a moment on how they did this particular survey on the River Severn But there still are some challenges with getting the data, making sure it is quality data, and processing that with multiple instruments, inclusive potentially of LiDAR. And then there's no immediate way to see those results and visualize the river to understand the impact that you may have. And so the back end of our workflow is really giving you that ability to visualize and see your river and what is changing and actually what's impacting your river over time. So this is where WaterCube actually comes in. We provide a complete workflow for advanced data collection utilizing the latest acquisition technology on the market, aggregating that together to produce very quick results, and then taking that into state-of-the-art visualization software, our Cubeit software, for managing and visualizing that data. And so I'm going to hand it over to Nick so that he can talk about how they cubed the River Severn.
Thanks, Diana. So Nick here, and that's a picture of me down on the bottom left out on the survey. In the background you can see a couple of kayaks and a power boat as well, which we used on the Severn when we were doing it. We went out twice, and on the next slide you should be able to see how traditionally we used to do things. So traditionally we had to tow the M9 from one bank to the other bank. Just pretty much how you do discharge measurements. But then the way the WaterCube works is that you can have multiple instruments out at the same time, and we run them down the river in parallel. So we might have one and do it 5 times, or we might have, if we're lucky, we might have 5 of them at the same time. So on this slide that you can see here, we've got multiple track lines and from multiple instruments and multiple ADCPs all going down the river at the same time. And each one of these yellow lines is a track line from all of the ADCPs that are being working synchronously at the same time, so that we have all this data. And if we just look at the next slide on here, we should be able to see a zoomed in detail below the island, showing you some more detail about the track lines. There we go on the top left there. On the right is a picture of River Severn live, where we've gone down. We just started it at the very beginning of the day and collected all 3 of the kilometers of river. We did that in approximately 4 to 5 hours using 3 M9s, 2 kayaks, and 1 boat to collect all this data. Now the problem is how do we present all this data? How do we link it all together? And if we look at the next slide, more detail how we put it all together. So if you could go to the next one.
Do you have it up now?
There we go. So on the left is the depth sounding from each of the 5. So in other cases, we've used a rope from shore to shore above the weir to make it as safe as we could. We've used the power boat as well. And we've also used remote control boats. So 3 of us out here at the same time collecting data simultaneously and then bring them back together. So WaterCube, what we did then is we took all of this data that we collected within 4 to 5 hours one day, and we did it on 2 separate events, and we brought it into WaterCube. And this is a picture here of not only the depth but the velocity in 3D as we put it together. So this is bringing all that data back from the M9s and put it into one package so you can visualize it. And so now I'm just going to hand over to Professor Art Smith of the University of Illinois, that's been helping out with WaterCube, and he's going to tell you more about what we can see with this data that we went out and collected. Over to you, Art.
Okay. Thank you, Nick. My name is Art Schmidt. I'm, as Nick said, a professor at the University of Illinois, Urbana-Champaign, Illinois. And I have been working with river measurements, flow measurements, hydroacoustics for about 3 decades now. And a while back, talking with, in particular, John Sloat from WaterCube, and just he mentioned some of what they're doing, and got rather excited about some of the possibilities. And so I'm going to take today, I'm going to show some things in WaterCube and just some of the things that can be done with this ability now to visualize what's happening inside an entire reach of a river. So the figure I have up here now is inside the WaterCube software. And this one, we've coupled the long stream velocities. The higher velocities are in red, lower velocities are in blue, for this entire 4-kilometer reach of the river near Shrewsbury. And then we also have LiDAR data coupled with this. So from the LiDAR data, you can see some of the features of the floodplain, the area around the river, the roads and so forth, the bridge here leading to the river. And so it starts to let you put the river in perspective, but then also see what are my different velocities. And you're not limited to velocities. You could have water quality parameters. Anything that you're collecting from the river can be put in here. Let me show. We're obviously, because of the danger of getting too close, there's a little gap in the data right here. But this is where the weir is, and then we can take, if I rotate a little bit here, maybe you can get a little bit better three-dimensional perspective of the water levels coming in and then going down in the channel of the river there. So I'm going to switch now to a second view here. Actually, I think this is the one I wanted. So now we have the same thing. We have the velocities. And I cut up the DEM just to make it a little bit clearer and see what we're looking at. And let me keep things out of the screen here. And one of the things I want to show is this ability we can take and we can slice the river and some slices. And if you watch on the screen, you will see slices moving through the river. I'm sure here. And so we can take and look at the velocity distribution throughout the vertical at different places in the river. And so we're starting to be able to see what's happening. Where might I have concerns? Where might be things behaving one way or another? We can also change our slices. I'm going to go to a horizontal plane here. And I will start with an animation. We will just start from a little bit below the stream bed and let the slices move up. And so you'll see it starts to fill in up here the deeper holes, but we're not to where there's water everywhere. Now we're getting the entire stream. And so we're looking at the slices as we move from the bottom up. To make it a little bit more plain, I will shut off the contour map here. Let me get rid of this bounding box, shut off the contour map, and go through our slices, these horizontal slices again. So what I want to illustrate here is the ability I can look at different parts, different levels, different vertical slices in my river. So for example, if I'm interested in a fish habitat study, I might want to know what are the velocities some distance above the stream bed. Similar type of thing for a scour, so it lets me look at this. What I'm going to do, though, for the most part today is we're going to talk about index velocity ratings, and I will use this as a case study as an example of what we could do with this. So we'll go back to the WaterCube software in a bit, but I want to give just a little bit of background for those who don't know index velocity ratings. Index velocity ratings are widely used at places where we don't have a good stage discharge rating. So this could be somewhere where we have backwater from a reservoir downstream, or a larger river that's flooding, anything where we get backwater conditions. It can be someplace where we have variable gate settings that can control and affect the relation between stage and discharge. Tidal influences, even sometimes a lower gradient stream that's highly unsteady, we can need an index velocity rating. So the basic idea is, instead of measuring the stage and estimating the discharge from the stage, we measured the stage, but we use a stage area relation determined by surveying the cross-section, and that will give us the area of the flow. We also put in an instrument that measures at some subsection of the flow, and we determine an index velocity rating, a relation between the mean velocity in the cross-section and the velocity we measure at this subsection of the stream. So then, by measuring an index velocity, we get a mean velocity in the cross-section. By measuring a stage, we get an area, and we use our relation, the discharge past the section is the mean velocity times the area. And when we get a good velocity index, this is a very powerful way to get our discharge. Unfortunately, not all sites work out well. This is an illustration of what we're trying to do. The blue box here is showing some subsection of the stream where we would measure the index velocity. In this illustration, it would be a side-looking instrument, so we have a slice in the horizontal in some part of the cross-section where we're measuring. The black lines here are the velocity isobels, so areas of equal velocity, and then we're showing with the dashed lines the profiles across and vertically at different points in the cross-section. So in velocity indexing, the fundamental assumption is that there's a very stable, well-defined relation between the velocity we're measuring in this index location and the mean velocity in the cross-section. If that holds, we get a good relation. If it doesn't hold, we're in trouble. But there's a lot of things that can affect this. Changes in flow conditions may change that velocity distribution. Changes in the geometry may do it. The distribution may change with time, things like scour sediment buildup in the channel. Our velocity distribution can change with fluid conditions. Think of a tidal stream where I have a density gradient or a thermal gradient in the stream that can affect it. Or things like variable gate settings, and I'll show an example of this a little bit later. The other thing I want to point out is something that's not presented much, but it's very important for velocity index ratings, is the SNR, or signal-to-noise ratio. So what I have shown here are two different velocity index ratings. The one in the black line is where our velocities that we're measuring are large compared to the mean velocity in the cross-section. And I'm calling that a high signal-to-noise ratio. So the slope of this rating is small. We have to multiply the measured velocity by a value less than 1 to get the mean velocity. The dashed blue line is a lower signal-to-noise ratio. The velocity we're measuring is smaller than the mean velocity, so we have to multiply it by a value greater than 1 to get our mean velocity. And so let me take now, I'm going to illustrate, in the vertical axis we have two lines. These are illustrating there's always some error in measurement. There's turbulence, there's different things, so no measurement is the exact truth. So there is some degree of error when we measure a velocity. If we have a high signal-to-noise ratio, even though there's a large change in the measured velocity, it results in a very tiny change in the mean velocity from this rating. We have that slope is small, and so it diminishes the error as we go from the measured to the rating. On the other hand, the lower signal-to-noise ratio, the steeper slope, the same uncertainty in velocity results in a larger error in our index velocity. And so when we're looking for a velocity index site, we want this high signal-to-noise ratio. So I'm going to show you some of the things we're looking at. Here's some data collected near Shrewsbury. These plots, and I'll show you in the Cubeit software a little bit later where we get these, and we can look at these live, but these are just two of the slices from along that reach we looked at. And so what I'm plotting here is the dimensionless velocity. So this is the velocity at any point in the cross-section divided by the mean velocity. So the orange and red colors are a high signal-to-noise ratio. We've got a large velocity relative to the mean. The greens are a value of 1. At that point, the flow is about at the mean velocity. And the blues are small values. In fact, some of the blues are less than 1. So in both of these, we have a large signal-to-noise ratio. However, on the left, you'll notice this bank here. I would anticipate this is near a meander or some other sort of sediment deposition. The channel geometry is shoving this maximum velocity over near the right bank. And, excuse me. And so I would expect at lower velocities, this peak area would move back more towards the center. At higher velocities, it will move even further to the right. And so because it's moving in the cross-section, it's likely to change that relation from where we measure to the mean as this moves. So I would not view this as a good potential site. This next site, we actually have two different high velocity sites. And again, this is after the island. The flow is merging but not completely mixed yet. And so as the flow condition changes, we may have one high velocity cell, we may have two, but we're not going to get a single unique good relation. In contrast, the first site I picked here was this one on the right. We've got a good strong signal. We've got signal-to-noise ratios or dimensionless velocities about 1.5. We're a fairly symmetric channel. It's a somewhat wide part of the cross-section. I was going to look more at that until as I went down the river, I saw this site. Now our core velocity in a symmetric section is a very large part of the cross-section. Even if it moves a little bit, we're going to get a very good signal, and we're going to have a stable relation. So I would expect this to be a very good velocity indexing site.
And all this data here this is from the WaterCube software, and this is from the Shrewsbury data that we collected.
This is the Shrewsbury data you collected a while back, and then these are just some of the slices from the Shrewsbury site from WaterCube. This is one time down the river. I'm now going to show results from a study done on the Snake River in Idaho. They had a velocity indexing site. In fact, I think it was near this first cross-section. And when they changed how they operated their 3 turbines, their index velocity rating went downhill very badly. And so they went out, they did 4 measurements under 4 different conditions, different flow conditions, different seasons, different water elevations. And what I have here is 4 slices from the exact same site under those 4 different flow conditions. So you'll notice the very different dimensionless velocity patterns. Clearly, as the flow conditions change, your center of maximum velocity is moving. So depending on where you're measuring, you're going to get a very dramatic change in that index velocity rating. In contrast, from the same data, just a different location in the stream, we identified this site where you have a very consistent pattern of where the maximum velocity is, the lower velocities near the banks, and any real river will have some variability, but this site is going to tend to be very stable. So if there's some concern about your site, doing multiple passes before you actually spend all the money to put the instrument in can be very valuable. So I want to show a little bit of this now in the Cubeit software. So what I have done here is I have zoomed in on that site where I said this would be a good one near Shrewsbury. And once again, I am going to pull up those slices.
So those two cross sections we can see on the screen there, how far apart are they in distance?
I would have to go back. Well, let's see. I have it right up here in my origin. I think we're about 150 meters here. You know, I've got the origin in easting and northing, but I'd have to look. Oh, I'm sorry, closer to 400 meters looking at the northing. So 400 to 500 meters. So we're maybe a half kilometer of the reach here, I believe.
And all those colors you have on the screen with the contours, they're representing velocity and not depth, right?
These are dimensionless velocities. So it's the same thing we looked at before. I've got the scale from a plus 1.7 to a minus 0.5. And then we have the 3D plot, the volume of the dimensionless velocities everywhere. And then I can also look at these slices moving through the reach. And so these are the same sort of slices we looked at before. So our hydrologists are used to going out and looking at a river, looking at the surface, looking at the stream bank, the plan view, and trying to identify where is a good site. Now, instead of just looking at the surface and the channel bed plan form, they can actually look at what's happening down inside the water. So we're getting a view here, but it's still a sequential view. It's one slice at a time, which our brain doesn't work really well with. So we can also, in the Cubeit software, these are all the dimensionless velocity slices from the upstream end all the way down the channel. So I just have all the slices pulled up side by side here. And we can just start to look at these and look for what is going to be a good site, what might not be as good a site. Where are we getting that strong signal, more of the red? Where are we getting things that are well centered in the channel? You'll notice some of these just sort of splotchy. It's not consistent as we move downstream. So for a very short area, we might have something good, but then we go a few meters downstream and it started to change.
So Art, just to confirm here, each of these vertical columns are discharge and measurements made on 4 separate events, 4 separate days. But
no, I'm sorry. This is Shrewsbury. So this is one event. This is, you're reading this just like a book. So this is a cross section. This is the next slice downstream, the next slice downstream, and so forth. And in the software, you can pick what sort of spacing do you want. I believe these were set up every 1 meter, but you can say every 1, every 5, every 10. And from all those data collected, the run of river and the ones, the transect type measurements merged together, the software puts together all these cross sections. So I'll scroll down a little further here. You'll notice we have some high velocity, but we have this dark blue band. We have an eddy here. We're just downstream from the weir, and so we have an area of some circulating flow. We're going to come a little bit further here. Here's some of the cross sections I picked before where we have that buildup of deposition on the left bank and the velocity profile near the right bank. And then now we're starting to break into where that island is. So you see we're forming 2 cones of the key velocity. And now we actually have the 2 channels either side of the island. And then we come back. The channels are going to merge together a little bit later. But you see we still have an area where we have 2 separate maximum velocities and actually a little bit of a shear layer, this negative velocity between the 2, until a little further downstream it mixes. And so I can continue, my hydrologist can continue to look until we see some of those sites where this is now looking like a good velocity. We have, and I think these are some of the sites I pulled up. You can see I'm now a distance of about 1,160 meters downstream from my weir. I've got slice numbers. I have UTM coordinates. A mean speed here of 0.59, a maximum of about 0.98, a depth of mean depth of about 2.5 meters with a maximum of 3.5. So we have the data here. I can pick different sites and look at and see what might be good. And so this is just illustrating how your hydrologist has more information to apply their expertise and where would be a good site for this. I'm going to now switch to the Snake River site. And when we pull this up, you'll notice we have a table. We have data for every slice, so I can look at it in tabular form or slice at a time. And I pulled this figure up at the top. What I'm showing here is the centerline distance and then the discharge determined from all these measurements as we move along the stream. And so you'll notice, again, 4 different dates, 2 in August of 2014, 1 in February 2014, 1 in February 2015, and then very different flow conditions. We had 2 turbines running. These we had just 1 turbine running. I can also change my y-axis to the water surface elevation along the reach. So we're seeing here's our water surface slope, but you'll also notice that even the 3 at the same flow condition, we had a change in the water level. So we have a seasonal difference, August to February, different water elevations and different flows. I can then pull up this matrix view, and I want to make my columns, instead of slice number, the date. So what I've just pulled up here, this is what you were thinking earlier, Nick, is each column here is a different date. Each row is the same slice, the same cross-section location. So now I have the ability, I can look my entire river. Here's some of the ones I showed before where you can see where the velocity is moving from the center out to the side. By the way, I should have pulled this up first. Let me give you an overview of where we're at. So I'm going to move this a little bit. This is the LiDAR and the dimensionless velocities at the site. We have the dam and reservoir up here. Here's a spillway, which is not being used. In fact, it's very rarely used. Here's a powerhouse with 3 turbines. And then in the LiDAR, you can see a road coming down and then a bridge here. And near where this bridge is where the old velocity index site was. And I showed a few slices, but what happens depending on which of the 3 turbines is being run, near the bridge, the maximum velocity moves from one bank to the other. And so that's why they were having the problems. So by looking at these data, again, you can see here the maximum velocity is near it would be the right downstream bank. A different turbine running, it's more in the center. As I scroll further downstream, and let me go a little bit here, we're getting to some of these points where no matter what the flow condition, we're getting very similar velocity distributions. And so that's telling me we've got much better sites. Some of these in here are where I thought might be a very good site for velocity and flow conditions, different seasons, different turbines running, different combinations of turbines. We're getting a very consistent pattern over time. So this was a site where doing multiple runs helps to identify a better site for velocity indexing. So with that, that's pretty much what I had on velocity indexing and how this software gives your scientists, your hydrologists and engineers the insight for this application. There are a lot of other applications that can be done with this, but beyond the scope of today's topics. So I think I'll hand it back to Nick and Diane now.
Thank you, Art.
You're just going to hand it back to Diana now to take you through the next slide, which is up on the screen now.
So what Art has shared with you is the environment, which is Cubeit. And Cubeit is a software application that is powered by TechPlot. We have partnered with TechPlot to bring this together and customize and optimize it for the water resource industry. And so WaterCube is bringing this to market and, of course, partnering with Xylem to bring all of the different views and aggregating the data together through our processing services, which then seamlessly bring this into our Cubeit software for you to visualize and do all of your different analyses. So the 4 different types of processing services that you can do, since we showed complete digital elevation models that you saw that Art shared with you, both of the Snake River and CJ Strike Dam. But we also did a run-of-river course on the River Severn, pulled in all of that LiDAR and created a digital elevation model for that as well. But that's something that typically our customers would want to do comparative analysis over time, or look for stream power or site selection for monitoring, as well as potentially for their modeling efforts to compare that spatial data to specific models they're developing. So that's one application for this. And another is to take just a smaller slice of that river, and that's the one to the right here, and create what we call a higher precision subcube. And this is where you may want to study that velocity index site or a placement of a monitoring station and look at it over different conditions. But we can also do more of a deeper data collection and higher precision analysis on this so that it's a smaller section of the river. On the bottom left, the ability to also go across bank to bank and do some traditional transect work, but taking multiple runs, 4 to 6 runs across, and projecting it to a single vector is still very, very common practice and can be used in habitat studies and 1D models. And then bathymetric surveys. So this is something very common that HydroSurveyor does today with the M9s, and we can bring multiple M9s together if needed on a very broad section of river for miles and miles or kilometers, and create those views for you from a bathymetric standpoint, but also in reservoirs or lakes where you need to look at volume and area tables. So those are some of the processing services that we provide, and then we create those views in Cubeit and deliver that to you so that it's a seamless process for you to visualize and analyze your data. And so the next slide, I think, is opening things up for a little Q&A. Nick?